But in 8.5 and 8.6, we're going to start talking about probability. So 8.5 focuses on the fundamental counting principle. So it says, if the first event can occur in m different ways, and the second event can occur in m different ways, then the number of ways that the two events can occur is m times m. So a lot of what we're doing in this section is multiplying our outcomes together. In this section, there's a few things that I'm going to expect you to know that are like common sense things. So as we get into example 3, it says how many different pairs of letters from the English alphabet are possible. Well, how many different letters do we have total? 26. That you got to know. So there's 26 letters. We're also going to talk a lot about cards, kind of as we get more towards 8.6. We'll talk about a deck of cards. Does anybody know how many cards are in a deck? 52. How many suits do we have? There's 4 sets, not counting jokers. So just 52 cards. There's 4 suits. So how many hearts would we have? There's 4 different suits. How many hearts would we have? 13. So there's 13 of each suit. We'll practice more. So if you're not super familiar with it yet, we'll get to it. But also on Canvas, I'll post a PDF of like a deck of cards laid out so you can kind of see it. And like I said, we'll get more into that tomorrow with 8.6. But deck of cards is something that's important to know too. So let's get to example 3. How many different pairs of letters from the English alphabet are possible? We have 26 letters total, so 26 options, but what does it mean to be a pair? How many are in a pair? 2. So we're talking about how many pairs of letters, so 2 letters at a time. So I could have AA, that would be a pair, AB, AC, AD, but it would take me all day to write them all out. But we're going to use our fundamental counting principle strategies. So we're going to be multiplying. How many different letters could I put in that first spot here? 26. I could put A through Z in that first spot. What about in the second spot? 26. I could put A through Z in the second spot. We're going to multiply these two together. So 26 times 26 would be 676. Now, the wording with these questions is super, super important. With this whole section, you got to pay attention to the wording of the question. Lots of word problems we're going to be doing, so read the question carefully. If this question said that the letters cannot repeat, so if there was no repeating, how many different letters could I put in that first spot? I could put 26. I could put A through Z in that first spot. But let's say I had A in the first spot. And I can't repeat, so I can't also have A in the second spot. So now how many different letters could we put in the second spot? 25, 1 less. So if there were no repeating, it would be 26 times 25, which would be 650. Perfect. Let's look at example 4. It says telephone numbers in the United States currently have 10 digits. The first 3 are the area code, and the next 7 are the local telephone number. How many different telephone numbers are possible within each area code? Note that at this time, a local telephone number cannot begin with a 0 or 1. So we have a 10-digit number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the first 3 digits are the area code. And the question's asking how many different telephone numbers are possible within each area code. So we're just focusing on one area code here. So our first set of numbers is 954. That's not changing. What can change are the next 7 numbers. Now it says that a telephone number cannot begin with a 0 or 1. Well, how many digits total do we have that could be in the first number here?
8.
It would be 8, because how many digits total are there? 10. There's 10 because we have 1 through 9, right? So the 9 and 0. So we have 10 digits total. But out of those 10 digits, the first one can't be a 0 or 1. So it could only be 2, 3, 4, 5, 6, 7, 8, 9. So it could only be 8 different numbers for that first spot. What about the second spot here? How many different numbers could we put here? 10. We could put 0 through 9 here. There's no restriction on what our second number has to be. It doesn't say that our numbers can't repeat, so we don't have to worry about that. So we have 10 different numbers that could go here. What about in the third spot? Another 10 different numbers that could go there. What about the fourth? 10, 10, 10, 10. So all the numbers after the first one, because the first one was the only one that we had a restriction. It couldn't be 0 or 1, but it could be any other number after that. So we had 8 different options there. But every other number, we had 10 different digits that we could put in that spot. So we just multiply all of these together. So we have 8 million different phone numbers in each area code. Let's do one more. So let's say we had a 4-digit ATM PIN. And let's say that the last digit had to be an odd number. So last digit is odd. So we've got a 4-digit PIN. How many different numbers could we have as our first digit in our PIN? 10. We could have 0 through 9. What about the second digit? 10. We could have 0 through 9. What about the third one? 10. We could have 0 through 9. What about the fourth? 5. Awesome, because there's only 5 digits that are odd. We could have 1, 3, 5, 7, or 9 in that last spot. So 5 options there. So we multiply all of these together, and that would give us 5,000. Next, we're going to talk about permutations and combinations. So a permutation, the order matters. So permutation, the order matters. In a combination, the order does not matter. So an example of a permutation would be like, how many different ways can you win a race for first, second, and third? Or how many different ways can you finish a race? So like the order that you end in the race matters. If it was like, how many different ways can these people be selected in a play? The order matters. You can't be both first and second in the play. So the order would matter of which position you are. An example of a combination would be like if you were picking people from a jury. Like if I selected 5 people out of this class to be on a jury, it doesn't matter if you're the first person picked on the jury or the last person picked on the jury, you're just on the jury. Or if I was selecting people, or if I was picking like apples into a basket, it doesn't matter if it was the first apple in the basket or the last apple, it's just apples in the basket. So permutation, the order matters. Combination, the order does not matter. So here it says a permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. Example 5, it says it explicitly in the question, how many permutations of the following letters are possible? So since this is a permutation, the order matters. How many letters do I have total here? 6. 1, 2, 3, 4, 5, 6. So how many different letters could be first? 6. But let's say we put A first. If A is first, A can't also be second. So how many different letters could I have be second? 5. If we put F second, so if A is first and F is second, how many different letters could be third? 4. What do you think about for fourth? 3, 2, and then 1. So we would just multiply all of these together to find the amount of permutations for our letters. So this would be 6 times 5 times 4 times 3 times 2 times 1, which would be 720. So the number of permutations of n elements is given by n factorial. We could have said that this was just 6 factorial, which would have given us the same thing. So in other words, there are n factorial different ways that n elements can be ordered. So this is if we have 6 elements, so we had 6 letters here, but we had 6 positions for them. Now it's a little bit different when we have n elements, but we're only taking r at a time. So if I said how many different pairs of these 6 letters that I had, it would be different. So permutations of n elements taken r at a time, we're going to see in example 6. It says 8 horses are running in a race. In how many different ways can these horses come in first, second, and third? So how many places do we care about? 3, first, second, and third. How many horses do we have that could finish in first? 8 horses. But let's say the red horse came in first. The red horse can't also come in second. So now, how many horses could be in second? 7. And let's say the blue horse came in second. So the red one's in first, the blue one's in second. How many options do we have for third now? 6. So we multiply 8 times 7 times 6. So that would give us 336. So this question isn't like example 5, the one before. What would make it like that question would be if we had 8 horses and it said how many different ways can the horses come in first through 8th. If we cared about every position of the race, then we would just do 8 factorial. But here we only care about the first 3 positions. So we're only taking r at a time. Now we have a formula for this. You could do it this way where you write out the places and you know that we have 8 that could be in the first, 7 in the next, 6 in the next one. But the formula is on the next page. So it works it. So the number of permutations of n elements taken r at a time is given by this formula here. So n factorial over n minus r factorial, where n is the total elements and r is the number that we're picking, I guess. The number that we care about. How many are we picking at a time? So in that last question, we had 8 horses total, but we only picked first, second, and third place. So n would be 8 and r would be 3. It works it out for us here. We have 8 factorial over 8 minus 3 factorial. So it's 8 factorial over 5 factorial, which ends up just being 8 times 7 times 6, which we get 336. So again, you could do it either way. You could write it out with your spaces or plug it into the formula. This is actually a button in our calculator. In my calculator, I would have to do 8 first, so the total. Then I have a button that is NPR, and then I would click 3 and then equals. To find this NPR button in my calculator, I click on the PRB button. So that PRB is for probability, which we're getting into now. So I click on the PRB button. You might have to scroll to get to the NPR button. Then you'd click on the second number and equals. If you can't find it in your calculator after we do the notes, I'll show you how. Next, we're going to talk about the number of distinguishable permutations. Distinguishable permutations, it's going to ask you for that word specifically. It'll say distinguishable permutations. If it asks for distinguishable permutations, it wants us to divide out the repeats. And I'll show you what I mean when we get to the next example. So distinguishable permutations, divide out the repeats. So looking at example 7, it says, in how many distinguishable ways can the letters in banana be written? So it uses that word distinguishable. When we have distinguishable, we do the total factorial over the repeated factorial. How many numbers how many letters total do we have in banana? 1, 2, 3, 4, 5, 6. So 6. We have 6 factorial on top. Then we want to look and see what's repeating. Does B repeat? No. What about A? How many A's do we have? So I'm going to divide it by 3 factorial. And then what about N? How many N's do we have? 2. So I also need to divide it by 2 factorial. So anything that's repeating, we divide it by that factorial. So you could put this into your calculator. In that same PRB button, there's an exclamation point, so you could do factorials in your calculator. I'm going to write this all out and simplify it by hand. So we have 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1. Do I need to put the 1 if I'm just multiplying by 1? No, we don't need to write it because times 1 would just be itself. And then 2 factorial would just be 2 times 1. Do we need to put the 1? No. So we can simplify here. I have a pair of 3's that'll cancel, a pair of 2's that'll cancel. And then I've got another solo 2, so I could cancel that out with 2 from the 6, but I'd be left with 3 there. So I divided 2 from 6, but I still have 3. So now I'm just multiplying 3 times 5 times 4. So 5 times 4 would be 20, times 3 would be 60. So we have 60 distinguishable permutations. So we had said in combinations, the order is not important. So it says that ABC and BAC are equivalent because both sets contain the same 3 elements, and the order in which the elements are listed are not important. So we would only count one of these 2 sets. So when we're finding combinations, we got to divide by a little bit more. So our formula is n factorial over n minus r factorial times r factorial. So we just have to make sure we divide out the overlap because these would be the same. So this, in our regular formula, it would count them as separate ones, but for combinations, thank you, we just have to divide out the overlap. So same thing, n is our total amount of elements, but we're only choosing r at a time. And again, this is a button in your calculator, so you could either just put it into your calculator, but we'll work it out using the formula too, just so we can practice. So let's look at example 8. And how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? It tells us the order of the 3 letters is not important. So it's super important that you pay attention to the way that the question's worded. It's not going to be like a combination, or it won't say combination or permutation every time. So here it says that the order is not important. So we know that this is a combination. So how many letters total do we have here for this question? 5, A, B, C, D, and E. So we've got 5 total. But it says in how many ways how many letters are we choosing? 3 letters be chosen from the letters. So 3 would be our R. So we have 5C3. You can put this into the calculator. I'm going to use the formula just to practice. But if you want to throw it into the calculator, you can. You'll end up with the same answer. So we have 5 factorial over 5 minus 3 factorial times 3 factorial. Bless you. What is 5 minus 3 factorial? Or what's 5 minus 3? So this would be 2 factorial. I'm going to write it all out to simplify, just because I think that it's fun to do it by hand. So we have 5 times 4 times 3 times 2 times 1, but we don't need to put the 1. 2 factorial would be 2 times 1, but we don't need to put the 1. And then 3 factorial would be 3 times 2 times 1, but we don't need to put the 1. If you want to write it all out and then from this step put it in the calculator, you can do that. Just make sure you put the denominator in parentheses. You need to know how to use your calculator. I'm going to simplify this more because, again, I think that it's fun. So the 3's cancel, the 2's cancel, and then 2 goes into 4 2 times. So we just have 5 times 2 left. So what would be our number of combinations here? 10. Question? Okay. Let's do B. It says a standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? After the cards are dealt, the player may reorder them, so order is not important. It tells us that the order is not important, so we know that this is a combination. So we need to know what our N and our R is. So how many cards total do we have? 52. And how many are we choosing for our hand? 5 cards. So R would be 5. So we have 52C5. Now you can put this into the calculator, but we're just going to practice using our formula. So we have 52 factorial over 52 minus 5 factorial times 5 factorial. What's 52 minus 5? So this would be 47 factorial. So I'm going to work it out by hand. I'm not going to go 52 through 1. I'm going to stop when I get to 47 because I see that I have a 47 factorial on the bottom. So we have 52 times 51 times 50 times 49 times 48 times 47 factorial. So I'm going to stop here because I know that that's going to cancel out with my 47 factorial from the bottom. And then I have 5 factorial, so that'll be 5 times 4 times 3 times 2 times 1, but we know that we don't need to write the 1. So our 47 factorials will cancel. I'm going to do some more simplifying by hand here, but if you want to just throw this all into the calculator, you can do that. But if you do it all at one time, make sure you put the denominator in parentheses. 5 goes into 50 how many times? 10. 4 goes into what? 48 how many times? 12 times, perfect. 3 goes into what? 3 goes into, does not go into 52. Goes into 51 how many times? 17. That works. You could also say 3 goes into 12 4 times, so you could have canceled out with the 12 too. But 3 goes into 51, we said 17 times. And then 2 goes into what? How many times? 26. So now we're just multiplying 26 by 17. 26 times 17 times 10 times 49 times 12. Now if you want to do it both ways just to check your math, you totally can. Do it both ways, but make sure you put the denominator in parentheses. So 26 times 17 times 10 times 49 times 12. So this would give us 2,598,960.